Okay, this is the 2008 question 8 exam. A fuel cell can provide powerful buses. It's a phosphoric acid fuel cell. So it's an acid fuel cell. You've got hydrogen ions. The electrolyte is concentrated phosphoric acid, and the reactants are hydrogen and oxygen gases. So hydrogen and oxygen. And it's producing water. So it's a classic fuel cell. If you balance this reaction, you've got two oxygens here, so you need 2 water molecules. That makes 4 hydrogens, so you need 2 hydrogen gas molecules. If you look at the states, it's a gas, and the state here, gas. Okay, so your overall equation is just a normal one. Okay, hydrogen over here, hydrogen molecules. They're sharing their 2 electrons. So they're going to lose those electrons. This is the fuel over here. All of your fuel cells have a fuel and oxygen. This is your fuel. They're going to lose their electrons and become hydrogen ions, so 2 hydrogen ions. So therefore they're going to lose their electrons. The electrons flow. This is the most important thing with any of these. Which direction are the electrons flowing? So they're coming from the side that loses the electrons is the anode, and oxidation is the loss, reduction is the gain, cathode. So this is the anode, this here, which is porous, and this is the cathode. Okay, so the electrons will come over to this side, and our oxygen is, each oxygen atom is sharing 2 electrons to make a double bond. Instead of sharing with the other oxygen, they're going to get their own. So if they did get their own totally, they would become oxygen ions, 2 oxygen ions, but they're not going to totally get their own electron, they're going to share it. So the hydrogen that is formed over here, the hydrogen ions, move across the electrons over here, making it more negative. The hydrogen, the positive and the negative balance. So the hydrogen move in this direction. So the oxygen kind of get the electrons because in a water molecule, instead of sharing equally, like in the oxygen atom, they're getting more of the share of the electrons. So if we looked at oxidation numbers, you can see that there's 0 to start with, and then the oxygen becomes -2 and the hydrogen becomes +1. So it's like it's gained, and this is like it's lost. So if we do, these reactions should be quite easy. Anode, oxidation. Just remember, which side do I put my electrons on? Where is the arrow? So the arrow is here. You're losing them. Reduction is the gain. So the electrons have to be on that side of the arrow. So you've got your hydrogen gas molecules losing electrons to become 2 hydrogen ions plus 2 electrons. Another way of checking that the electrons are on the right side, there's no charge over here, so you need no charge over here. So 2 positives, 2 negatives makes no charge. Make sure you put the negative on there. The states here, hydrogen, so you must have states for half equations. Alright, so the oxygen is getting the electrons, and it could have been oxygen ions that were formed, but it's water. It's always water for these. So you've got 2 oxygen atoms, so therefore you need 2 water molecules, which means that you've got 4 hydrogens, so you're going to balance those by adding 4 hydrogen ions over here and 4 electrons. Whichever side the hydrogen ions are on, the electrons will be on as well. So 4 positives, 4 negatives balance out. Don't forget your states. So this is a gas. Use whatever is given in the picture. So the water is gas, and the hydrogen ions are aqueous. This is also in your data booklet. Okay. Next question. On the diagram, draw an arrow to show the direction which these ions, these negative ions, move. So you're losing negative on this side, so therefore the negative must move over that side to balance it, to add the negative. Okay, this question. A particular cell operates at 0.92 volts. How much energy in kilojoules is delivered per 1 mole of hydrogen in this fuel cell? Okay, so you need some way of connecting the volts to the energy, and we haven't really learnt this. So we do know energy from your calorimeter. If you want to calibrate your calorimeter, you put a certain voltage into the calorimeter, certain current for a certain time, and it will heat the calorimeter with a certain amount of energy. So we can connect volts to energy. So we know the volts. So the thing is, there's no current or time here. So we need something that has current and time in it. So the other thing that we know is Q. Q equals current and time. So we need some way of finding Q. So Q, if we know the number of moles of some chemical that's been made, we can work backwards to find Q. So we know the number of moles of hydrogen gas that's being formed. We want it per 1 mole. So if we work out the number of moles of electrons, then we can use the number of moles of electrons to find Q. So the equation that we'll eventually be heading towards, the number of moles of electrons, is Q divided by Faraday's constant, or Q divided by 96,500. So if we can get the number of moles of electrons, we can find Q, and we can get the number of moles of electrons by relating mole ratio with hydrogen. So the number of moles of electrons is twice the number of moles of hydrogen. So the number of moles of electrons, 2 times the number of moles of hydrogen, and the number of moles of hydrogen is 1. So we have 2 moles of electrons, which is what's here. Alright, so if we want Q, if we rearrange Q, it's divided on that side, take it at the other side and multiply it, so it's the number of moles of electrons multiplied by Faraday's constant, 2 moles of electrons multiplied by 96,500 gives us a certain number of coulombs. Alright, so here, this is the energy that we want. So we've got our voltage, 0.92. Now I'm going to be a bit lazy. This equals IT, or Q here. So I should write this out, VQ equals the energy. So we've got our voltage, and we've got our Q, 2 moles times 96,500. Okay, so if we look in the answers, because I'm too lazy, it's 1.78 by 10 to the 5, and this equation is in joules. So the question, just be careful, the question's asking for kilojoules. So you'd have to divide it by 1,000. So basically you're removing 1,000 off here, so it's 1.78 by 10 to the 2 kilojoules. Okay, by comparing the energy delivered per 1 mole of hydrogen in the fuel cell and the heat of combustion of hydrogen, so heat of combustion, you look in your data booklet. Calculate the energy efficiency of this fuel cell. This is a bit annoying because what they wanted was what percentage of the energy that you would get totally from the heat of combustion. That should be the total amount of energy that would be produced from hydrogen. What amount of energy of that energy is actually delivered in the fuel cell? In other words, how efficient is it? So they were looking for a percentage. So you just needed to look on in your data booklet. So you get 282 joules. You should, but our example that we did a minute ago, you only got 178. So the percent efficiency is 178 out of a total of 282 from your data booklet. That's a percentage, and you get, so it's 62% efficient. The rest of that would have been lost as heat. Okay, describe one advantage and one disadvantage of such a fuel cell compared with a petrol-driven car. They like these questions, you know, there'll be something like this. It's worth 2 marks, so it's worth making sure you get it right, because 2 marks from a multiple choice is a lot more effort than this. So fuel cells don't lose as much heat as petrol-driven cars because combustion engines are hot. They lose a lot of their chemical energy as heat energy rather than converting it to movement. So one of the advantages is that they're efficient. The other advantage, obviously, our product is water, whereas the product of this is carbon dioxide, which is a greenhouse gas, which is contributing to climate change. So pick one of those. So fuel cells are more efficient, energy efficient, because there's always a because. With any of these questions, there's always kind of 2 parts to an answer. Because the chemical energy is directly converted to electrical and little less lost. Or you could just say that the product is water compared with carbon dioxide, which is a greenhouse gas. So have the 2 parts to the answer. Disadvantage. Okay, so the reason that we're not all driving cars with hydrogen fuel cells, what do you know about hydrogen? Hydrogen is a flammable gas. So lots of problems with transporting and putting in petrol stations flammable gases, putting in your cars flammable gases, etc. So you need to just say, so it's difficult to transport and store the gas. Go on if you want to, because you need strong containers and to be aware of sources of ignition. I'm going on a bit, you don't need to write all of this, but you do need to say something about it. Something about it and something about why it's a problem, a disadvantage.